All right, we're going to start a new chapter today, and this is the third exam material, only one chapter, gases. There's a good bit of math in it, and I think that's why I kept it by itself. But I also want to call your attention to the lab that we're going to have next Tuesday on Boyle's Law. If you've got a bicycle pump, bring it, because we need to pressurize a 2-liter pop bottle to conduct the experiment. I've got one pump, but you don't have to share it.
I think I have 2 of them.
That'd be great. Yeah. Okay. Let's get on with gases. Let's see, is it moving? That's moving. And lock it up there. All right. I like to put a discussion of gases in my chemistry course as close to the front as possible. We had to get some of that chapter 1, 2, 3, and 4 out of the way, because those are essential things, but gases gives you a more historical perspective, because when modern chemistry started to develop in the 17th century, the primary focus on most of the physics and chemistry experiments in those days were on gases. And it should become fairly evident soon, if I don't happen to mention, that was the natural way to do things. They have the technology to deal with gases. All gases tend to behave the same way in many respects. So it was just a logical starting point. So first of all, what is a gas? Get that out of there. I don't know if I can. Come on. No, it's going to stay there, I think. I don't know why. Anyway, we have to remember at the very beginning, I wanted you to try to develop an intuition, a connection between the observable world, the macroscopic world, and the microscopic world. And gases are a really good place to hammer this point home, because we have to treat gases as if they're lots of particles there in a gas that has no definite volume and no definite shape. But the gas particles act as independent players. In other words, they don't form a crystal structure. They're not even close enough to slide past each one another and interact as you would expect in a liquid. Gases are by comparison very far apart, so they act. All the particles in a gas act independently. This says semi-independent, which is true. There is some interaction, but that's for another topic. So gases are, we know that they can be either atoms or molecules. They can be individual atoms, like the noble gases, good example. Or they can be molecules, like diatomic oxygen, nitrogen, fluorine, hydrogen, all those diatomic gases. They can be compounds, right? They can be like methane, carbon, hydrogen, CH4. They can be any type of molecule or atom, but they're moving really fast. And I hope to prove that later on. And that's one of the reasons that they don't interact very much, because they're moving so fast. The time of interaction is very short. So you don't get a lot of, come on in. You don't get a lot of, there's not a lot of time for either repulsion or attraction in a chemical sense. Another characteristic of gases is that they're miscible, which means when you put them together, you always get a homogeneous mixture, a solution, every time, no exceptions. You put two or more gases together, they always mix perfectly as a solution. And that makes sense when you consider that compared to the size of the particles in a gas, the distance between them is huge. There's plenty of room for everybody. They do have mass, though. And let's see. No, it must be the second semester. Second semester, we're going to take advantage of that fact, the mass of a gas. So that's all. That's the teaser. But because they have mass, each individual particle has mass. They have kinetic energy, and which is energy of motion. Remember the formula for kinetic energy? If you don't, I'm going to put it up here. All right, so the kinetic energy of any object in the physical universe is proportional to its mass and proportional to the square of its velocity. So if you know the mass, you know its velocity, you can calculate the kinetic energy of any object in the universe. With a few exceptions. When you get really small, this is Newtonian physics. So when you get really small, you got to go to quantum mechanics. That's something different. If you get really big, like black holes, then this kind of falls apart there too. But in between, and for our purposes, this calculation is true for any object. So you know that, I don't know, did anybody take driver's ed in high school? Okay. Did they teach you how the energy of your vehicle, if you double your speed, the energy quadruples? They didn't tell you that? Oh, okay. Well, they're falling down on the job. This is why. When you go from 30 to 60 miles an hour, it takes 4 times as much energy to get there. So that's why when you try to slow down from 60, it takes you like 4 times as the distance as it does if you're stopping from 30. Anyway, that's another characteristic of gases. And we have to assume that their motion is random. The reason we've got to assume random motion is because we can't track every particle. There's just too many of them. Even for a gas, where there's fewer particles in a certain volume of gas than there would be a liquid or a solid. But there's still too many of them. It would take a supercomputer, I don't know how many weeks, to calculate all the trajectories of the gas particles. Right, so we just assume they're random and we treat them statistically. All right. So what we're going to do in the subsequent slides is look at how the different gas laws work and how they various factors that define a gas interact with one another. We're going to look at, and exactly, in particular, we're going to look at 4 different descriptors for gases. Right? We're going to look at pressure, look at gas volume. We're going to look at the number of particles, like moles, that's my abbreviation for moles. And we're going to look at temperature. If you know these 4 factors about a gas, you can completely describe its behavior in a physical sense, right? We're not talking about chemistry yet. So I'll leave those up there because when we start talking about the gas laws, I'm going to go back to this one frequently. In the beginning, we're going to treat all gases the same. And that's going to be our ideal gas. Every gas behaves exactly the same under conditions that we're accustomed to. 1 atmosphere, room temperature, and with a range on either side, up or down on those factors. We treat those gases as ideal. And then we'll say a short word at the end about non-ideal behavior. We're going to solve problems with gas equations. That's going to be one of our main focuses in this chapter, is solving gas equation problems. So that's why I said at the beginning that this is going to be weighted heavily toward math. Right? It's not difficult math, but if you feel like you're weak in math, then you're going to have to build your skill as you go. All right, examples. Earth's atmosphere, of course, right? It's a solution of gases, primarily nitrogen, right? 79% nitrogen and 20% oxygen, and then a little less than 1% argon, and then some trace gases, carbon dioxide and water and other things. But the Earth's atmosphere, this gas is necessary for life, right? And we think of it in terms of the oxygen content, right? For heterotrophs like us, like animals, oxygen is essential for survival. But the nitrogen part of the atmosphere is just as essential for plants, because they need fixed nitrogen to build proteins, to build nucleic acids, to build all their structures. They need nitrogen and they need carbon dioxide. Carbon dioxide to a plant is food. So when we try to limit the amount of carbon dioxide in the atmosphere, we're starving the plants. We're going to say a few words about atmospheric pollution, right? It does exist, right? But it's not quite the type of pollution that the ruling authorities would have you believe. And it's worse in some places than others, like Los Angeles, right? Just one smog day after another, they say. And it's rare that they have clear skies. I'm going to try to set the record straight as best I can about pollution and global warming. Get up on my soapbox for a few minutes. It depends on how much time we have. Okay. The first descriptor of gases we want to define is pressure. So we're going to start with pressure. And pressure is actually easily definable. It's a force per unit area. And what we're trying to do here in defining these values is relate them back to the SI units, the fundamental units that we've discussed in earlier chapters. Like what's the standard for length? The meter, right? Okay. So the standard for area would be the square meter. Okay. How about force? What's the standard for force? Well, force is a derived unit, but it's the Newton, named after Isaac Newton. But Newton is also derived, right, from one of his equations. Right? His second law of motion is force equals mass times acceleration. So this force unit, this Newton, is actually equal to what's the standard for mass? Kilogram, right? So a kilogram. And then what's the standard for acceleration? Well, we have to derive that too. Acceleration is a change in velocity. Does anybody have physics in here? Physical science? Okay, so you remember some of this stuff. Okay, acceleration, we have to take velocity, meters per second. Those are fundamental units. And then if the velocity changes over time, then the second squared, because it's a change in velocity, meters per second change. So that's where this one comes in, meters per second squared. So this Newton is actually 1 kilogram meters per second squared. And then we take that and put it up here and derive another unit. Okay. And if we use these units, then this unit is the Pascal. Okay. What I'm trying to drive home here is that when we start using dimensional analysis in these unit conversions wherever they may occur in the equations for gases. And sometimes we have to go back to the derivation of the unit in order to get other units to cancel and derive the final answer in proper units. We can't just assume that the units are going to be right if we plug the values into an equation that we like. Okay. Have I told you the story about my friend in Baton Rouge? He was a mechanical engineer student. Tell you about him? He marveled at students in the classes that he took in mechanical engineering. They'd study a certain chapter on a topic, and they'd have several equations that were used in processing the data in that context. He said, but during a test, they'd forget everything they knew before, and they try to shoehorn data, information from a problem into the equations that they had used in that chapter. And it always come out with the wrong answer. And they come out with answers that would just made no physical sense whatsoever. Right? But that's as far as their thinking went. Right? It was what I would call muddled thinking, not clear-headed thinking. So this is an attempt to promote clear-headed thinking, right? All right, so that's the standard for pressure, that value, the Pascal. But pressure is one of those values that has been grandfathered in from several different directions. Right? In this country, pounds per square inch. Everybody knows that is pressure. And that's the value you get when you check the pressure in your tires. Or other parts of the world, they generally use pascals. Or even before that was atmospheres. And that's the one I think we're going to use that one primarily, at least for Boyle's law. Okay, so we're going to go back and look at the history of the measurement of pressure. In other words, the progression of these scientific investigations during the 16th and 17th and 18th century primarily moved along with developing technology. So when they were studying gases, the first technologies that developed were measurements of pressure and volume. Volume was pretty well understood and fixed and standardized by the time pressure came along, but we needed a way to measure pressure, and that's where the barometer came in, the development of the barometer. And we owe that to an Italian during the late Renaissance, Torricelli, Evangelista Torricelli. And all he did was they took a glass tube, and they were really good at making long, uniform diameter glass tubes in those days. And he either did it, I don't know if he did it or had it done for him, had a glass blower, just seal it off at one end. Right, so he took the glass tube and sealed it off at one end. Right, but before he did, he filled it up with, it would be this direction first, he filled it up with mercury. Okay. Mercury was cheap, commonly available in those days. And the nice thing about it was very dense. You needed a dense liquid. I don't know if he gave it some thought, probably did. Said, why don't I just use water, right? Water is really plentiful, right? We can make it pure by distillation. Well, as it turns out, if you're trying to make a barometer, and everybody knows what a barometer is, it measures atmospheric pressure. If you're trying to make a barometer to measure atmospheric pressure, he soon realized that you would need a glass tube at least 33 feet long. But mercury is And I painted myself into a corner. It's a whole lot denser than water. So it takes, you get a shorter tube, right? You get a tube about that long instead of 33 feet. That's why, you got any scuba divers in the family? No? It's a rule of thumb. Every 33 feet that you descend underwater adds another atmosphere of pressure on your body. Okay, so then he filled it up with mercury, right? Mercury is going to be like that, but it's a convex meniscus, not like water. Water is concave in its meniscus. Convex meniscus, and then he just put his thumb over it and then inverted it in a pool of mercury. Okay. Now this is the sealed end. Inverted it in mercury, and instead of staying up here at the top, which he might have expected, it dropped somewhere in here. And the distance between here and here is pressure of the atmosphere. Okay. And you notice that over time, well, actually, first thing he did was you could take it down to the sea level and the mercury would rise. He just marked a place on a tube and the mercury would rise. But if he went up the mountain, threw it in the back of his ox cart and went up the mountain, it dropped. So he reasoned that the cause of that change in pressure was how much atmosphere was above the barometer. And he was right. The more atmosphere that's above your barometer, the higher the pressure. So if you go to Denver, right, the pressure is going to be a lot lower. They're about a half a mile higher than we are here. We're about a half a mile above sea level. So the pressure is going to be lower here than it is in Myrtle Beach on an average day. Okay, so that was the barometer, measuring atmospheric pressure. And it didn't take long for this technology to spread throughout Europe. Everybody was using it. In fact, I want to make this point first. When there was mercury up here and he pulled his thumb away and it dropped, what's left? The first vacuum, right? There was something there, now there's nothing there. So that's a vacuum by definition. And he reasoned that the height of this column of mercury was offsetting the forces. The force that's due from the mercury is being offset by the force of atmosphere. And we know now that if you calibrate this thing in millimeters, right, on an average day, 1 atmosphere will hold that column up 760 millimeters high. Okay. So those are 3 different ways so far that we've been able to express pressure. One is the SI way with pascals. The other was atmospheres, and another is millimeters of mercury. Now, on the Greenbrier campus, we actually still have a mercury barometer on the wall there. But it's not good to move those things around, so I couldn't steal it. So ours, the one we have in the lab, is Android barometer. That is no liquids. Android means no liquids. Okay. With people also noticed that not just a change in height, but a change in the weather would affect pressure. So if you just sit it on your bench top and watch it day by day, you'll see as the weather gets bad, rain clouds move in, all that, the pressure drops. And when it passes and the clear skies come, it goes back up. So they associated, and it's still true today, high pressure is associated with good weather and low pressure is associated with bad weather. And really, really, really low pressure is associated with hurricanes. Okay, All right, I already said that. Inclement weather, rising barometers, fair weather approaching. All right, come on, here we go. So the normal atmospheric pressure has been standardized. In other words, when we need a conversion factor, we have an equivalence here. 1 atmosphere equals 760 millimeters of mercury. So if I have a value of, I don't know, 0.97 atmospheres, I can convert that to millimeters of mercury by using that equivalence, right? I need atmospheres on the bottom and millimeters of mercury on the top, like 1,760. So I can convert that into millimeters of mercury if I want. Okay. And this example is from Raleigh County Airport. One day it was what 694 millimeters of mercury, and we use the relationship to convert that into atmospheres, and we find that it should be less than 1 atmosphere. Yeah, 0.91 atmospheres. I used to work with a lady whose initials were BKW. Okay. But those are the what they call FAA abbreviations for the Beckley Airport, BKW. And if you go up to Winter Place, just down the road here, they're about 1,000 feet higher than we are. And by comparison, their pressure was lower, 669 millimeters, which is what, 0.88. Okay. And if you go down to Death Valley, then you can get an increase in atmosphere because you're below sea level. All right. So that's one type of conversion that we can do with our pressure values. Now, when we make measurements next week during lab, we're going to measure with tire pumps, and we're going to measure in pounds per square inch. So that's another, pounds per square inch is another way to measure pressure, force per unit area. And the relationship between pounds per square inch and atmospheres is 14.69. Pounds per square inch is 1 atmosphere. So we can make any type of conversion we want. We could use these two as an equivalence, those two as an equivalence, even pascals. Let's see. Weathermen use another one called the bar, which is pretty close to 1 atmosphere, but not exactly. So when they say this hurricane has a pressure of like 0.72 bar, then you know it's really low. And the lower the pressure, the more powerful the storm. Okay, there's the SI unit for Pascal. It's 1 Newton per square meter. And here's just a list of the others. Oh, inches of mercury. Forgot that one too. 29.92 inches of mercury. That's another way of expressing pressure. All right, there's the bar. Okay. So 1 atmosphere is actually 1,013 millibars, or actually the relationship between bar and Pascal is fixed. I think that's where they got it. 1 bar is 100,000 pascals. So when we put that together with the other conversions, then we come out with the millibar, which is actually, you'll see that on weather maps as millibar. Only you can't, I don't want to take up too much of your time, but when you look at a weather map, the coding that they use for pressure is a little different. Right? They don't just come out and say 1,013 millibars. It's a little tricky. But if you're ever interested, I'll show you how they do it. Okay. So 1 atmosphere is slightly more than 100,000 pascals. So Pascal is a small force compared to, right? We're a little less than an atmosphere right now. Of course, we don't feel it because inside and outside are at the same pressure. But if you go down and you try to go down and see the Titanic in a faulty submarine, then the pressure difference is significant. And they say when that what was it made of, carbon fiber, when that carbon fiber cylinder collapsed under the pressure, it happened in milliseconds. I mean, they were dead before they even knew it. So I guess that's merciful. They didn't suffer. So these are examples of converting from one to the other. And it's purely dimensional analysis, right? This particular example is working through a chained conversion, going from PSI to inches of mercury by way of two conversion factors. This one first, and then that one next. All right. So we're going to have some problems that we can work out with this, particularly in the review document. There are lots of these problems in there to give you lots of practice. And that converts to millibars. Okay, before we waste too much time on pressure. So it just depends on your focus. What are you trying to do? What's your particular discipline involved with? I mean, are you involved with weather? Are you involved with laboratory chemistry? Are you involved with manufacturing tires? You know, depends on what your business is as to which unit you're going to be using. This is just, you don't have to do this. Oh, there's the density of mercury, 13.59. It's 13.59 times the density of water. Right? Water is 1 gram per cubic centimeter on average. Right? So it's 13.6 times as dense as water, which allows you to shorten the tube. And the G is the physical equivalent of the acceleration due to gravity at the Earth's surface, 9.8 meters per second squared. Right? If you've had any physics or exposure in any way, you'll recognize that one. In this calculation, all it does is just it makes a series of calculations that takes the barometer and it determines the actual exerted pressure of a 760 millimeter high, 5 millimeter diameter tube or column of mercury. It takes that factor, that height, that diameter, and converts it into applied force. Right? And that just proves that the relationship between, let's see, 101.3 kilopascals. Well, those are all equivalent. And that's all that I was doing with that demonstration, is just proving that you could go from one to the other by way of fundamental and derived units. Okay, so now that we know how to measure pressure, how to express pressure quantitatively, let's get to our first law. This law was developed by Robert Boyle. I know you've heard that name before. In previous chapters. In the middle of the 17th century, Robert Boyle came up with this first expression of gas law, and it related these two factors right here, pressure and volume. That's what we're going to be doing on Tuesday. Now, one thing to remember is when we write these gas laws, in order for these two variables, in order for us to allow those two variables to change in response to one another, like we're going to change pressure and see what happens to volume. Okay, so pressure is the independent variable, volume is the dependent. And so if we put them in a graph, pressure will be on the x-axis and volume would be on the y-axis. And in order to do that, we have to hold these two constant. Okay, that has to be true. These two must be constant in order for us to derive the relationship between these two. What Boyle says is that when we do that, when we change the pressure and watch the volume, the product of those two variables is a constant. Okay, so what that means is if we increase the pressure, and this is constant, then the volume has to go down. Right? They're inversely proportional. That's the only way you can keep this constant. Right? If they both go up together, then the cake keeps getting bigger. Okay, so pressure, if we increase the pressure, volume must go down. Okay, so here's a plot of some hypothetical data, right? Experiment 1 says, all right, we set the pressure at 25 atmospheres. Actually, we're going to go from high end pressure and decrease the pressure. So as we decrease the pressure, volume should go up. And that's what we're going to show. 25 atmospheres and a volume of 4 liters. Right? Multiply those together, you get 100, right? So the next experiment, we're going to change the pressure to 20. And now the volume is 5. 5 times 20 is 100. And we do another experiment. Right? Still, pressure times volume is equal to that constant, 100. And we're plotting those points on the graph on the right as we go. Okay. Is this as far as we're going? We got to plot that last one. We didn't plot it. 4 and 25. There it is. Okay. Notice the shape of the curve. Pressure, volume. The shape of the curve is like that. And whenever you multiply two variables together to get a constant, it's always that shape. And that shape has a special name. I remember it from math or geometry, maybe. It's called hyperbola. Characteristic of a hyperbola is that this tail right here will never touch that axis. And this tail will never touch that axis. Okay. Now, when you were studying in math class, you probably had all 4 quadrants. And this one would have a mirror image over here. Remember that? Yeah. But for our purposes, that's all we need. Okay. So this inverse proportionality says that as one goes up, the other goes down. That's inverse. And what you'll see on a graph with an inverse proportionality is a negative slope. Only, I mean, where do you figure the slope here? Right? The slope is different here than it is here. Right? It's a changing slope. And anybody had calculus? No. Instantaneous slope. The slope of a line that's tangent to the curve. So if we're tangent right here, then it's the slope of that line. It's the slope of the curve at that point, the instantaneous point. Or if we fix it over here, it's a different one. Or if you fix it up here, it's a different one. But it's always negative, right? It's always negative. Negative goes from upper left to lower right, correct? Positive goes from lower left to upper right. So a negative slope means an inverse proportionality of your variables. Okay. Let's see. What are we going to talk about next? All right. Temperature and moles have to stay the same. Now, how did Boyle do it? Well, he used what was called, he went back to glass tubing, right, and used mercury. So he had a glass tube made, or he made it himself, I don't know which, and it's a J tube. This. Opened at that end, closed at this end. So he took Torricelli's tube and just bent it. And then he poured mercury in it. And of course, in the beginning, a little bit cooled up on the bottom right there. And then he poured some more, cooled up a little higher. Once it cooled up and touched that inner curve, then this gas in here was sealed off. Can't put any more in it. That fixes this one, constant. Now his experiments didn't take very long. So he could assume that the temperature was constant, room temperature, whatever it was. So he could do several of these experiments in just 15 or 20 minutes, and the temperature would be fairly constant. But if you ever have any doubt, right, you can always fix the temperature. Right? The easiest way, just make an ice water bath. Right? Ice and water together will always be, as long as there's solid ice, liquid water, and it's at equilibrium, the temperature will be at the freezing point of water. Right? So if you just submerge it in a water bath, then the temperature is going to be constant no matter what happens outside. That's one way to do it. And then he noticed that as he added more mercury, this side may come up to there, but this side was over here. It's always higher than this side. So the difference between these two levels here, this change in height, was a measure of the pressure on that trapped gas. Plus, since this is an open tube, atmospheric pressure. So the pressure on that trapped gas was the atmospheric pressure plus the difference here. Okay? So remember that when we do our experiment. We're going to measure the pressure inside our containment vessel, but there's also atmospheric that has to be added to it to get you the total pressure that's on the gas. And he did that. And he just measured the height, difference in height, as an indication of pressure. So this difference here increased as he added more mercury, and this distance here decreased as a measure of volume. So we used atmospheric pressure and liters in volume because we're familiar with those, but he didn't have to. This is a uniform diameter tube, so the volume is proportional to the height. So he used height here, and he used height here in millimeters plus millimeters from his barometer that he had sitting over on the desk. Just add those two together, and he just tallied them together and came up with this relationship. That's Boyle's law. Now, the thing about this inverse proportionality and the fact that it's a curve is scientists don't like curves. They're not very well behaved. They only use curves when they absolutely have to. So we try to figure out a way to take this data set and transform it so we get a straight line, right? And you remember doing that with the graphing. Yeah. Okay, so I won't have to beat that horse too long. But I will, for the benefit of posterity and those that watch this video later. We take this formula here, this is a constant, and we transform it using legal means, mathematical means, divide both sides through by volume, right? So that cancels this volume and leaves us with P over here. And now we got K over V. Well, we're going to factor out that V, 1 over, excuse me, let's keep the K here, K times 1 over V. Right? That's the same thing. Now what we have is Y equals MX plus B, and B is 0. That's a straight line. So what we need to do is plot pressure against 1 over volume. Okay, and when we do, we go through the origin, because that's our y-intercept, and we get straight line with a positive slope. Simply because this is y equals mx plus b. Okay. So what this slide is continuing to show us is, I think I've got them out of order, but nevertheless, this is true. And remember, whenever you do something to a variable, you also do it to the units. So if the units of this volume were liters, what would be the units of 1 over b? Liters to the minus 1. And anything to the minus 1 is the inverse, correct? Okay. So those would be the units here. And say this might be atmospheres. Okay. So let's talk about, should have written this up here, Boyle's law. So how can we use Boyle's law? Well, the simplest way to use Boyle's law is in what I call a before and after scenario. Right? What are the conditions before? What are some of the conditions after? And solve for the unknown condition. And what we do here is say, if this is the condition at the beginning, and it's equal to the constant, and this is the condition after, we measure the pressure and the volume change, and that's also equal to K, right? So we use the cumulative property, right? If A equals B and B equals C, then A equals C. So this one equals that one. This is the before, this is the after. Okay? Now, rather than measure everything, if we know these two conditions, right, we've got those measured, and we measure this one, then we don't have to measure volume. We can calculate because it's an equation in one unknown. We can solve for it. Right? And in the slide, we use initial and final. Right? So initial and final, same difference. And in this example, we calculate the final volume of a gas when 15 liters of gas at 500 millimeters of mercury suffer pressure drop to 125 millimeters of mercury. Then we can calculate the final volume. We just have to plug in the values and solve for the unknown. And notice also that the units of pressure don't have to be atmospheres. Right? As long as the pressure units are the same, they're going to cancel because it's a ratio. Okay. And the units of volume here are going to be the units of volume there. I need to correct this slide because the abbreviation for liters is not little l, it's big L. I inherited this slide set, so throw it off on somebody else. Okay, so suppose we have a system where we have 325 cubic feet. I'm going to have to pick it up if I'm going to get done. 325 cubic feet at 12 psi, squeezed to 240. So we squeeze to a moon volume. Now we're going to calculate this one. So we just put the values in, or we solve for the unknown, right? I think that's the way this animation goes. We solve for the final pressure, and then we plug in the values, and we end up with 6.24 psi. That's probably, we have to assume that 12 psi has 2 decimals on the end of it, right? Otherwise, we've just invented 2 significant figures in our answer. Okay, the next one came along a little later. And the Frenchman is responsible for this one, I believe. Charles' law. Yeah, Charles' law. Now for this one, we're looking at a relationship of volume and temperature.
So moles must be constant again, and pressure must be constant in order for this relationship to be worked out. Okay? And in order to work with temperature, that's where the technology comes in. Before Charles could do this work, we needed a reproducible unit of measure and a device that would measure temperature of any substance. And that came about, first it came about with Fahrenheit, right? Fahrenheit temperature. And then followed closely behind that with Celsius. Have I talked about the temperature units yet? Previous chapter. Okay. So Fahrenheit was interested in living systems, but his system was a little different. And Celsius was more interested in chemical and physical properties. His was different. But what Charles discovered was his law didn't work if there were any negative temperatures in there. Negative temperatures just screwed everything up. So what had to happen was another scientist by the name of Kelvin fixed the problem. In other words, he took the Celsius temperature and just moved the 0 point down to absolute zero. So every temperature in the Kelvin system is positive. So when you're dealing with temperature in this chapter and successive chapters, unless I say otherwise, you always have to convert temperature to Kelvin. It's not Kelvin degrees, it's just K. Okay, so if you do that, well, actually, Charles didn't have to wait on Kelvin to formulate his law. It's just that it's not very useful unless you can get rid of the negatives. Okay. What Charles discovered was that with a change in temperature, which is the independent variable, gives you a change in volume, which is the dependent variable. And so you get a data set here. You change the temperature and you keep the pressure in the moles constant. So how do you do that? Well, you have a device, a uniform diameter, and a piston in it. Okay? And on that piston, you place some weight that's heavy enough so that the atmospheric pressure changes don't matter. Let's say we put 5 kilograms. Right? And that'll shrink it down to a certain point. And that's where you start at a given temperature. So you measure the temperature surrounding this containment. I think it would have been difficult for him to stick a thermometer in here. So I think he just had a bath of some kind around it and changed the temperature using that bath, either an air bath or a liquid bath of some kind. So you got the temperature and you know the height here, plus you've got a uniform diameter. So if you know the height, you can calculate the volume. So I measured the volume of a trapped gas, and that fixes the number of moles in here at different temperatures. And he came up with a data set. And what he discovered was that as temperature increases, the volume increases. So they have a direct relationship. So as temperature increases, this is the X value, volume increases. Or you can write it this way: volume divided by temperature equals a constant. And if this is going to be a constant, then as one goes up, the other one has to go up. So the moral of that story is, if you have two variables and the product of the variables equals a constant, you have an inverse proportion. If you have two variables and the quotient of the two variables is equal to a constant, you have a direct proportion. Okay, and this is what it looked like. And notice that he could go negative temperatures if he wanted to and decrease the volume. And you can plot that on the graph. But when you try to put them in here, it kind of falls apart because negative numbers don't give you the same constant that positive numbers do, right? If you let the temperature go negative, then the constant's going to change. Right? So the relationship is true, even with Celsius temperature. But the calculations won't work unless you have absolutes, all positive temperature values. And that's why we need Kelvin. All right. So here's what Kelvin did. He took all this data, and this is a really, really simplified, abbreviated version of what Kelvin was doing. Kelvin was working with thermodynamics. It was a very, very new concept and part of physics that was developing at the time. And this was only a small part of what he did. Anyway, he proposed this new system based upon the Celsius temperature scale, only we moved the zero. And he found zero by plotting what would happen if you extended that line all the way down to zero volume. And so at zero volume, theoretically, the temperature would drop to zero. I mean, the volume would drop to zero and the temperature would drop to some other value. And that's where he found it, where it intersected the x-axis right down here, 273.15, occurred at zero volume. But of course, we've never been to zero volume. You can only get to zero volume if gases have no volume, if the particles have no volume. But we know they do. Right? So you can only get down so small, then you can't get any smaller with a gas because the molecules kind of get in the way. But theoretically speaking, that's where he fixed his 0 point, minus 273. Let's see if I got the other scale on here. I guess not. But what that tells you is that temperature in the Kelvin scale is equal to the temperature of the Celsius scale plus 273. And we're just going to use 273, not the 0.15. You can use 0.15 if you want, but I never do. Okay. So we introduce Charles' law in terms of before and after. This is before and this is after. There you go. Similar to Boyle's law. And if you know 3 of these values, you can calculate the 4th one. Okay? You just have to recognize which law is applicable. That's the trick. Okay. So I'm going to breeze through this one because I'm running out of time. You just solve for the unknown, plug in the knowns, and get your answer. And here's another one. I'll sort of go through the animation slowly so the video will capture it. But notice in this case, we've converted our temperature to Kelvin. And whenever you, in fact, in this chapter, get in the habit. Whenever you see temperature in Celsius, just go ahead and convert it to Kelvin. Okay. So there's another example. We'll do more of these examples when we do the review on Tuesday. We'll do a review on Tuesday and then go in the lab, do Boyle's law. It'll be fun. Boyle's law is easy. It's an easy lab. You just have to wear your protective clothing and your eye protection in case the bottle explodes. I've only had one explode one time, and I learned my lesson. It was a bottle that we had used several times before. It had been weakened, and it blew up. So now I take a bottle, we use it once, and I cut it and throw it away. Okay. I think I've got plenty of them. You don't have to bring any extras. Unless you got some extra pop bottles. You got any 2-liter pop bottles at home? No, okay. Yeah, I'm kind of running short of them too because I stopped drinking pop. I guess I'm gonna have to start doing it again. I'm gonna run out of bottles. Okay, third law I'm gonna talk about is Avogadro's law. I think we've mentioned Avogadro before. When we introduced the concept of moles. Let's see, let me just write it again up here. Okay. For Avogadro's law, we're drawing we're allowing the variables that we're allowing to move, to change, are volume and moles. So that means pressure must be constant and temperature must be constant. Okay. So I don't have time to go into the Karlsruhe Congress discussion, but needless to say, Avogadro's work in this area solved problems for chemists in universities and in industry in Europe in particular in the 1860s. At that time, chemists only understood reaction chemistry in terms of masses. Masses of reactants give you masses of products. So when something went wrong, they couldn't figure out what was wrong because the reaction doesn't take place, right? You've learned that when we balanced equation. Reaction is not balanced in terms of masses, it's balanced in terms of numbers of atoms and molecules. So that's where Avogadro's law came in. And his expression says that that relationship, right? So it's a quotient of two variables. It's a direct proportionality. As the number of moles increase, if the volume is constant and the temperature, let's see, oh, excuse me. Sorry. If the pressure is constant and the temperature is constant, then as we increase the number of moles, then we increase the volume. Right? We use a similar type of arrangement to Charles' law with the movable piston and make the pressure constant, and then we hold the temperature constant with controlling the environment. Then you can put so many moles of gas in there and you can get a change in volume. Now we had to be able to determine how do you determine the moles of gas, right? That was the trick. And in fact, I'll have to admit, I don't know how Avogadro did it. I think it was all based on Avogadro's hypothesis. And I've showed you that one with the two cylinders. Okay. Yeah. So once you know that volume, temperature, and pressure are the same in those two cylinders, you know you have exactly the same number of particles in each one. I think that's how that's his jumping off point for determining the number of moles that you put into a cylinder. All right, we can solve this equation just like before. V1N1 equals V2N2. Okay. And you can solve problems with it just like the others. Right? You can rearrange for the unknown and plug in the values you do know and solve for that unknown. Now this one, it doesn't matter. The temperature is not a problem, right? Because it's constant. So you can use any value you want for, well, N we think of as moles, but it could be anything that measures numbers of particles. I don't know what that would be other than moles. Or any units of volume would work also. And this example relates this law to a chemical reaction. Notice this balanced equation where we decompose 2 moles of ammonia and get 1 mole of nitrogen and 3 moles of hydrogen. The relationship of the moles before and after are the coefficients. Right? If we start off with 2 moles of ammonia to begin with, then when the reaction is complete, we end up with 4 moles. So we changed. We went from 2 to 4, correct? And if we start off with 35 cubic feet, then there we have an equation in one unknown. And we can solve for that value. Well, we can intuitively see that if the number of moles doubled, then this is going to double. So that one should be 70, right? Here we go. Here we go. And there we go. 70 cubic feet. So after the reaction is complete, the cylinder should have expanded, should have doubled its size. As long as we keep pressure, temperature constant. Okay. So we can take these laws and combine them. And here's the way I do it. We know the relationship between pressure and volume, right? Pressure 1 V1 equals pressure 2 V2, right? Okay. Well, we also know that volume and temperature are related. Okay. We also know that volume and moles are related. So that's a combined equation. This expression is equal to that expression, as long as we keep the before and after unadulterated by any other processes. All right. So this begins with Boyle's law. Okay. And then we add Charles' law. We stick the temperature in there. And then we stick Avogadro's law relationship in there. And that's our combined law. We're still before and after. So it's like, just like before, only now you've got 8 variables. And if we know 7 of them, we can solve for the 8th one. So in this case, you don't have to decide which law to use. But if we know that moles and temperature are the same on both sides, then they cancel, and we got Boyle's law. Or if we know that pressure and moles are the same on both sides, we got Charles' law. Okay. Ideal gas equation. Okay. If we take this and we say that P times V is a constant, V divided by T is a constant, V divided by N is a constant, we just combine all of those into one constant. So we have a constant here. Well, both of these are equal to the same constant. What if we don't know the before? We only know the now. We only know the after. That's where the ideal gas equation comes in. Let's understand ideal gas first. Okay. It's often referred to as a perfect gas. And what that means is it obeys all of the laws. There are no deviations with any of these laws that we've discussed. We also must assume, and I alluded to this with Kelvin's experience, point molecular volume. What that means, when you're studying math, you start with a point, and then you have a series of points, and that makes a line. Right? That's one dimension, linear dimension. If you go in the other direction, then you define an area. Okay? And if you go in a third direction, you define the volume. Right? So that takes in all 3 dimensions from that position. But if you've got a point volume, it has no dimensions. Right? The volume of a gas with point volume is 0. So ideal gases are assumed to have a 0 molecular volume. We know that's not true, but we're talking about a perfect gas, an ideal gas, not a real gas. They don't interact with other gases. What we mean by that is they don't have any repulsions or attractions when they come close to one another. In other words, we know they're going to bang into each other, right, because they're moving really fast. And there's lots of them. So they are going to strike one another. But when they do, they act just like billiard balls. right? Conservation of momentum. They just go boom, like that. No interactions whatsoever. That's a perfect gas, an ideal gas. And I already said that one. Oh, I thought I was describing the first one. The first one says that all pressures and temperatures, you remain a gas. And that's sort of a corollary of does not interact. Because if you get interactions between gas molecules, then when you squeeze them and you make them cold, then they start to interact. And they may even condense into a liquid or go to a solid like carbon dioxide, like dry ice. That's a real gas. Ideal gases are gases forever. Okay, we know that real gases liquefy and solidify. If we put enough pressure, we cool them down. We do know that they have actual volumes, so they're never going to follow Kelvin's line all the way down to zero volume. That would never happen. And they do interact with other gases. They also interact with the walls of a container. Kind of left that one out of the first one. They interact with the walls of the container, and it's a good thing they do, because if they didn't, we couldn't measure the pressure. Right? Stick a gauge in there and register no pressure, we think there's no gas in there. But they do interact with the walls of the container and with any gauge we put in there. So we depend upon that real gas behavior to measure these pressures. So when do gases behave ideally? When can we treat them as ideal? Well, under conditions of low pressure and high temperature. And I don't know if I put this one in there. Low moles. In other words, don't put a lot of gas squeezed together into a small volume, because then the chances of interaction increase and you get more real behavior and less ideal behavior. So when are these conditions? When do we experience these conditions? Well, 1 atmosphere is considered low pressure, right? You go to like 1,000 atmospheres, that's high pressure. High temperature, room temperature is considered high temperature. Why? Compared to absolute zero. 293 would be 20 degrees Celsius. So at room temperature, that's pretty high temperature. And then low moles are actually related to pressure. So if we have low moles, we're going to have low pressure. Okay. So the ideal gas law, we're going to develop that from the combined law. Right. Suppose we don't know after, we don't know before, one or the other. We just know now, the state. Well, if we standardize the units and the values for these numbers, and we know how they're related, then we can calculate what that constant is. So for one example, we're going to say, all right, we're going to standardize it 1 atmosphere and 1 mole of gas, right? And the temperature is going to be 0 degrees Celsius, or 273 K. Okay. Now, under these conditions, 1 mole, that temperature in that atmosphere, the volume is going to be 22.4 liters. Now, with all these properly related, we can calculate that K, and we give it a special symbol, R, like the ideal gas constant. And with these units of measure, we have 0.08206 liter atmospheres per mole K. Remember, we do the same thing to units that we do to the numbers. If we're going to divide these two and multiply those, then atmospheres times liters divided by moles times K. Those are our units. And in that case, this expression becomes that value, and now we don't have to know before and after. We just have to know what's right now. Since this is a constant, if we know three of those, we can calculate the fourth one. But with this constant, the units must be taken into consideration. Temperature has to be K, moles, atmospheres, liters to use that value. And what you'll see it like this most often. PV equals nRT. We just move these two over here. N and T times R and then PV on that side. That's the ideal gas equation. It was first proposed in the middle 1800s by Emil Clapeyron. Clapeyron did a lot of other stuff, and he was active in thermodynamics too. There's your ideal gas equation. And it can be, if we're using these units of measure, that's what you get. If you're using different units of measure, in fact, SI units, you get Pascal cubic meters divided by mole K. And Pascal cubic meters is equivalent to a joule. A joule is a unit of measure, a standard unit of measure for heat or energy. We're not going to use that one yet. We will eventually use that second one, right? When we deal with the discussions of thermodynamics. Let's see. Right, I'm past time. And I got a lot more to do. So if you got to go, then go. But I need to finish this so I can get it recorded and posted for you. I'm not sure if we're going to have time to do a pre-lab on the Boyle's law. So this is the second one, I think, that you have to have your notebook prepared. Okay, this is going to be a formal report. So set up your notebook because I'm going to check them again. And if you need some pre-lab information, instruction, there should be a video in Brightspace, historical video that I did earlier for other classes. And that should help you with understanding the concept. Okay. So, see if anybody, nobody else showed up. So we're missing Alexis. That's it. We were just missing Alexis. All right. So I'm going to keep rolling. All right. What we're doing here with these animations is just solving for different unknowns. And you know how to do that by now. It's just if you know everything on the right, then you're solving for the one on the left. You can also solve for, if you want to know ratios, let's see, new temperature, okay. If you want to solve for ratios like moles per unit volume, then you can also solve for N divided by V, and then you only have to plug in pressure R and T. Let's see, if we solve for R, we did that before when we were developing the equation. All right, so here's an example where you know the conditions right now. You don't know before and after. And if you see a word problem, that's one thing where gases are concerned. If you look for before and after, then you will see two different measurements of the same unit of measure in at least one place. If it's a single gas law, it's in one place. But that's a way to tell if you've got a before and after or a state version. And in this case, we only have the 2 moles, 37 degrees, and 50 liters, and we want to find out what's the pressure of this system, right? First, we have to be sure, are our units correct? 2 moles, that's correct. Degree C, no.
change it to Kelvin. Liters, that's correct. And remember, the units are all based upon that R value. Liter atmospheres per mole K. So that tells you the units that you need in your variables. Okay, we're going to rearrange for pressure. Right? And then in the equation, we've incorporated the change of 37 degrees Celsius into K. And that used 273.16, which is all right. And the moles cancel, liters cancel, temperature cancels, and you're left with atmospheres. So we can calculate the atmospheric pressure under those conditions. Here's another problem. We're going to convert temperature. Let's see. Yes, convert temperature. And then we're going to convert pressure from millimeters of mercury to atmospheres. All right. And then we can use the formula. Okay, rearrange, insert the variables, and solve for the unknown. Canceling units. 7.919 moles. Okay, so that's two types of problems. We've got before and after problems, and we've got state problems that can be solved with what we've learned so far. Now, this problem, we're going to introduce solutions of stoichiometry using the gas law. So the question is, using this equation, right? Yeah. That arrow is pointing the wrong direction. It should be this way. Liquid plus oxygen. And this equation is balanced, right? 2 oxygens, 2 mercuries. All right. We want to calculate the mass of mercury 2 oxide needed to produce 220 cubic centimeters of oxygen. Right? We want to know the mass required to do that. Okay. So remember, in a balanced equation, we can't move anywhere unless we know moles. So we got to find out how many moles of oxygen are represented by that value. Right? Are we given enough information? Well, at 25 degrees, and this is equal to 220 milliliters, which is 0.220 liters. Right? So now we have volume. Right? How about temperature? 25 degrees C plus 273 equals 298 K. You got temperature, volume, temperature, and we're solving for moles. So volume, temperature, we need pressure. Is pressure given? 740 millimeters of mercury. 740 millimeters of mercury converted to atmospheres, we just divide by 760. And that gives us 0.9737 atmosphere. Now we can use our formula, right? PV equals nRT. Solve for N is PV over RT. And then we can put in the pressure, 0.9737 atmospheres. Volume is 0.220 liters. R is 0.08206. Liter atmospheres per mole K, and then temperature is 298. Now they add 0.6. That's okay. Okay, and then we calculate N. Okay, that's what we're doing here by rearranging the equation. Okay,
0.008755 moles of oxygen. Then we use the stoichiometry. 0.008. That would be 8.755 times 10 to the minus 3. And the ratio here is 1 oxygen for 2 mercury 2 oxides. That's where the conversion factor comes from. And what we find is with this calculation, which we're incorporating the conversion as part of the calculation. So that's that second part over here. See, I'll point to it right here. This is the molar mass of HGO. And that will tell us, once we calculate that out, that will tell us the mass and answer the question. Oops, went too far. There we go. 1.87 grams of HGO will give us oxygen, 220 cubic centimeters of oxygen under those conditions. That's how we use the gas law in stoichiometry. Let's see. Oops. Was this a different question? Oh, what volume of mercury was produced? Right. In this case, since we know the moles of oxygen, we can find out how many moles of mercury, right? Twice that is the number of moles of mercury. And then we can convert mercury to grams, and they use the density of mercury to find the cubic centimeters or milliliters of the mercury. And that's what this bottom calculation has done. Right, so it's not very much. Right, it's about a quarter of a cubic centimeter, a quarter of a milliliter of mercury is all you have left. All right. So this Dumas method references what I talked about earlier, where we know that gases have mass. We're going to use the mass of the gas plus the gas law in order to determine the molar of mass of a gas or a volatile liquid. Right. So this person, Jean-Baptiste André Dumas, not the same Dumas that wrote the Three Musketeers. This is a different Dumas. We're not going to spend a whole lot of time on this because in the second semester, we actually do a lab using this procedure. But in order to determine the molar mass of any compound, you need the mass of a certain number of moles. Right? So we can weigh a container that has a gas in it. We can weigh it before and we can weigh it after. And then we can measure the conditions surrounding that gas that influence the number of moles that are contained in that volume. And once we calculate the moles using our gas equation, then we have mass and moles, we can calculate the molar mass. Let's see. These are various facts about Dumas. If we, MW is molecular weight or molar mass. So if we have those two equations, and molecular weight equals mass per unit moles, then what we can do is combine those two equations, right? If we solve this one for moles, right, bring it over here, mass divided by molecular weight, and we substitute this in here, actually this value will go in there, then PV equals mass over molecular weight times RT. Then we can solve for molecular weight. Molecular weight then would be equal to mass RT divided by PV. So that's all we have to do. We have to determine the mass of the gas, the temperature at which we collected it, the pressure, atmospheric pressure, and the volume of the container that holds the gas. And we can calculate the molecular weight of a volatile liquid, a gas or a volatile liquid. All we have to do is when we put the liquid in there, we have to evaporate it until there's nothing left of it but vapor inside. And then we can use the gas laws to finish it off. All right, here's an example. And I'm already running real late, so I'm not going to go into a lot of detail. But under these conditions, we have a 250 milliliter flask fitted with a pinhole and a lid, because gases have to be contained. We put a pinhole in there so that we don't get backflowing of atmosphere. We want, only thing in that flask we want is the volatile liquid that is turned into a vapor. And the only thing left in there is a vapor. So we weigh it before at 325 grams, and then we weigh it after at 326.4 grams. And the difference is the weight or the mass of the gas. And that's the first value that we've got there, the mass of the vapor that's in that container. Now we need to calculate the moles. So we use this gas equation and we measure the pressure. There we go. We got the mass, we got R. We measure the temperature at 99.7 Celsius or 372.86 Kelvin. Then we measure the pressure, the atmospheric pressure, 710 millimeters of mercury, convert that to atmospheres. Right? Why? Because R is in liter atmospheres per mole K. And then the volume, we know is the volume was determined to be, I'm looking, I guess we're assuming 250 milliliters in the flask. But you have to determine that experimentally. Right? And we'll do that next semester when we get to this lab. All right. So when we solve this equation, we find that the compound is 152.98 grams per mole. That's the Dumas method. Okay. This particular problem, you can see as a before and after. Notice there are 50 liters, and the question is, what's the final volume? So we start off with 50, and we want to know the final. If we change the temperature from 250 degrees Celsius to 25, and we measure the pressure change from 750 millimeters of mercury to 900 millimeters of mercury, that's obviously a before and after. So we can use the combined equation for this one. And that's what this procedure is going to do. All right. Okay, we're putting the combined equation there on the right. And we're solving for the unknown. The final volume is what we're going to know. So then we have to do some conversions. Right? We have to convert temperature to Kelvin. We don't have to convert pressure because those units will cancel. We don't have to convert anything else. But what happened to the moles? Right? Why is there no value for the moles? Because the gas was confined and there's no reaction occurring. There's no addition of moles or subtraction of moles. So the moles cancel. Right? They go out. And we only have to use what's left. So now we know under these conditions, when the conditions change, as indicated, you get a change of volume, and now from 50 liters down to 23.75 liters. Okay, here we've got that decomposition again, where ammonia is decomposed into nitrogen gas and hydrogen gas. So we want to calculate the final pressure of the system when 25 cubic feet of ammonia at 400 millimeters of mercury and 25 degrees Celsius is rapidly heated to 500 degrees, and the vessel expands to 30 cubic feet. Right. Calculate the final pressure. All right. We have to take into account a change in the number of moles also. Right. This is a before and after problem, but we also have to introduce values for the number of moles that have changed. So when we have the before and after equations, there we go, and we solve for the final pressure, notice that the moles final and the moles initial must be considered. The moles final will be 3 plus 1, or 4, and the moles initial will be 2. And then the other values, of course, have to be included. So you see there, right here, is after moles and before moles. And this is initial pressure, and final pressure is not there because we're solving for the final pressure. There are the temperatures and there are the volumes. But when we solve for that equation and cancel the appropriate units, we ended up with 1728.7 millimeters of mercury is the final pressure after the reaction. All right. So what we're getting to now is one more law. This is Dalton's law. Of partial pressures. Dalton's law of partial pressures simply states that when you have a mixture of gases in a container, then the pressure, the total pressure in the container is equal to the arithmetic sum of all of the pressures of the individual gases. Right? So if you have one gas here, its pressure is that. If you have another gas, its pressure is that, and that, right on out to however many you have. And that's what we're looking at here. If we solve pressure using the ideal gas equation, right, remember, pressure then would be nRT over V. Okay. So that's what's happened here. We take the total pressure, right, would be the number of total moles. And if we keep the temperature and the volume and R is a constant, if you keep those all the same, I think the next, here we go. We collect all of our terms, then what we get is the total pressure is proportional to the number of moles of each of the gases. So this is another way of expressing Avogadro's law. Remember, pressure in moles. But actually, that's not, because Avogadro's law is volume in moles. Okay, but in this case, we show mathematically that the total pressure is due to the summation of the moles of all the gases times the gas constant, the temperature that they all experience, divided by the volume that they all experience. So the total pressure is proportional to the total moles. And another way to express that is a term called mole fraction. Mole fraction. Mole fraction is simply referencing one particular gas. Let's say it's the first gas at pressure 1. Is the number of moles of that gas divided by the total moles. It's a fraction. It's less than 1. Okay? And you can do that for each one. Each one of the moles. And they have to equal 1. And if you count for every gas that's in the container, then the fraction of each one added together will be 1. Now, what can we do with that? Well, if we take this compound, C3H5N3O9, which is nitroglycerin, and we allow it to detonate, it completely decomposes into these 4 gases: carbon dioxide, water, nitrogen, and oxygen. And that's the mole ratio in this decomposition. So we've gone from 4 moles of nitroglycerin to 29 moles of total gases. Now, if we're given these conditions, 100-liter vessel, 25 degrees Celsius, 20 millimeters of mercury, we detonate it, and it expands to 110 liters, and the temperature rises to 400 degrees C, then what we want to know is, what's the final pressure? Right? So the final pressure is going to be this arrangement, like we did before. Solve the final pressure with the before and after equation. And we know that the moles are the important factors. Right? Notice the moles here. The starting moles of that gas are 4. When we finish, we have 29 moles. And what we calculate from this set of ingredients is that the pressure increased from 20 millimeters of mercury up to 297. So it increased by a factor of 15, almost. That's where the force of nitroglycerin, that uses as an explosive, that's where the usefulness of the nitroglycerin comes from, is its rapid expansion from 4 to 29 moles. Not so much the temperature, but the change in number of moles of gas increases the pressure very rapidly. So if we know that we know the total pressure, right? What are the partial pressures of carbon dioxide, water, nitrogen, and oxygen in the vessel at the end? Well, remember the mole fractions are proportional to partial pressures. Right? So if the total pressure is 297, then the mole ratio of 12 carbon dioxide to 29 total gives us the mole fraction of carbon dioxide, and then all we have to do is take that fraction of the total pressure, and that gives us the pressure of carbon dioxide, which is 123 millimeters of mercury. We do that for each one, and we find that carbon dioxide produces the most pressure increase in that decomposition, that detonation of nitroglycerin. Water contributes quite a bit also, but nitrogen and oxygen quite a bit less. And if we add those partial pressures up, then we should get the total. We get pretty close to the total. We're off by a little bit experimental calculation error. All right. Now, up to this point, we've discussed only laws. Remember, at the very beginning, we said a law was just a description, either in words or in formulas,
a description of what happens under certain conditions, with no attempt to explain why. Now, with the kinetic molecular theory, we're going to try to explain why these gas laws actually work. Okay. But we need postulates, right? We have to nail down what we think the theory is, and then we can apply it. Right, so here are the basic postulates of the theory. We've got a large number of particles, atoms and molecules, in the gas, whether it's pure or a mixture, it doesn't matter. The particle size is small compared to the distance between the particles. And so their volumes are almost insignificant. But the gas particles are in rapid, constant motion. We might add random also. And since the collisions with other particles are inevitable, then the collisions with the particles and the collisions with the pressure must be accounted for in our theory. We also have to assume that the average kinetic energy of the gas particles is the same at a given temperature. If you increase the temperature, the kinetic energy increases. Right? In fact, temperature is a measure of the average kinetic energy of any substance in which you place the thermometer. But because we can't track every one of them, right? The distribution at any temperature, the distribution of particles, number of particles, with temperature is going to be sort of a bell-shaped curve. In other words, most of them are going to be in this range. Right? Some of them are going to be very high, some are going to be very low. And what we're saying is that for the purposes of convenience and simplicity, we're saying that this average here, we're going to assign that to all the particles. Well, actually, it's not that temperature. That's the peak temperature. We're going to take a weighted average of that. So it'd be somewhere in here. We also must assume that there are no interactions among the particles. There's intermolecular forces. Inter means between, between particles. Right? If we were talking about inside the molecules, we'd say intramolecular. But intermolecular is any forces between the molecules is insignificant. All right. So what we're going to do now is create this hypothetical where we have just a few particles, and we're going to do some calculations. And what we're trying to do is demonstrate how we get this average value. All right. The kinetic energy of each object can be determined based upon its mass and its velocity. Remember the kinetic energy formula. And that's what E sub k is referencing. I write big K, big E. This slide uses E with a sub k. That's kinetic energy. We're going to use 7 bowling balls that are 5 kilograms each. Right? And there we go. So those 7 balls have different velocities, right? There's a slow one, there's a fast one, and then some in between. And if we calculate the kinetic energy of each one of those, then you get that list: 250, 1,000, 2,250, 4,000, 6,250, 9,000, and 12,250 joules. That's the energy that they have. Each one has its own energy. We want to know what's the average energy. Well, if we calculate the average velocity of each one, it would be simply 10 plus 20 plus 30 plus 40, 50, 60, 70 divided by 7 is 40 meters per second is the average velocity. If we try to calculate the kinetic energy from that, we get one value. If we calculate the average kinetic energy from the individuals, then that's 250 plus 1,000 plus 2250 on a cross divided by 7. The average kinetic energy is 5,000 joules based upon our individual calculations and then take the average. If we take the velocity, the average velocity, and try to calculate the velocity, we rearrange the equation so that we could calculate the velocity based upon kinetic energy equals 1/2 mv squared. Then if we use that and we calculate the average speed of each one based upon its energy, right? We put the energy value into that equation and we calculated that the average velocity based upon that calculation is 44.7 meters per second and not 40. So the true weighted average of the velocity for those 7 objects is 44.7 meters per second, not 40. All right, how do we do that? If we have the velocities, how do we calculate the average velocity so that it agrees with the energy calculation? It's a process. Let's see. Let's go back. It's a process called root mean square. So if we have 10 through 70, as the velocity of each particle, then in order to get a velocity without having to calculate the energies and going back through this process, we use a process called root mean square calculation. So what does that mean? Well, root mean square in order to make sense of that, you work from the end and come backwards. You square each one of these values, right? So we square velocities at 100, 400, 900, 1600, 2500, 3600, and 4900. That's the square of the velocity. Then we take the mean of that one, right? So we get the mean of those square values. And I'll have to use my calculator to do that. 100, 400, 900, 1600, 2500, 3600, and 4900. And we want to take the average of these. So I've got a value of 1.1525 times 10 to the 4th divided by 7. And that's 1.6464 times 10 to the 3rd. And now we've done this, we've done this. Now we need to take the root of it. So we take the square root of this value. And that gives us 40.57. That's not what I expected it to be. I thought root mean square would give us 44.72. Okay. Well, I can't explain it right now unless I've made a mistake in calculation. That's possible. But this root mean square calculation is supposed to be the quicker way to get to the value. All right, we're still talking about the kinetic molecular theory. So now what we want to talk about is, first of all, just one particle in a box with random motion. If we address the energy of the particle in one direction, right? If the particle is moving, let's draw a box like this. And we've got a particle, say, here. And it's moving, it's not moving this way or out. Say it's moving kind of off in an angle like that. Well, we can't calculate its energy in one of these XYZ directions. We have to take into account its motion in each of those directions. So we can parse it out so that it's moving a certain velocity this way, it's moving a certain velocity this way, and it's moving a certain velocity out. And if we combine those, 1/2 m mu squared in x, y, and z, mu there is velocity. Then we can combine those and find out what the energy of that one particle is. But we have to know the x, y, z directions. It's called vector analysis. So don't worry about that right now. If we do that for a mole of particles, right, then we would have to say something about the average of those XYZ velocities times a mole, and that would be the kinetic energy of that mole of particles. So the root mean square this is an expression for the root mean square, right? We take the mean, we take the square of the particles, like I showed before. Then we take the mean of that squared value. Then we take the square root of that value, and that's the mu RMS, root mean square. So what we've determined, and we don't have to go into the derivation of this formula, but what we've determined is that the root mean square is related to the particle temperature, the gas constant R, and its molecular weight, or its molar mass, with this expression, square root of 3RT over molar mass, is equal to the root mean square velocity of the particles. Now, in this case, we have to use a different R value, 8.3145 joules per mole K, because we're talking about energy now. We're not talking about liter atmospheres. And so that one has to be in the R. Okay, we're going to use that relationship to calculate the average velocity, the root mean square average velocity of air at 37 degrees Celsius, or 310 degrees Kelvin. So what we need is an average molecular weight of air, or molar mass of air. And that turns out to be 29.02 grams per mole. That takes the composition of air and all the different molecules in it into account. And notice that we have to use SI units. We can't use grams per mole. It must be kilograms per mole in order to use that formula. So that's why we made that conversion. Then we substitute into the equation with 3 times the R value times the temperature divided by the molar mass, and then take the square root of all that. And what we end up with is that at that temperature, 37 degrees, by the way, what is 37 degrees? It's not room temperature. Room temperature is 20 degrees. 37 degrees Celsius is body temperature. So if we took a great big deep breath of air and held it there for a few seconds, temperature would equilibrate, it would be at 37 degrees, and that's how fast particles would be moving, 516 meters per second. Right? Convert that to miles per hour, and that's what we've done here. The reason I wanted to convert it to miles per hour is to get an idea, what's the relationship between the speed and the speed of sound. And in fact, 1155 miles per hour is faster than the speed of sound. Right? Now, if we do this for helium rather than air and substitute helium motor mass in there, then we get the fact that the helium atoms are moving faster. They're at the same temperature, so they have the same average kinetic energy, but in order to do that, they have to move faster because they're smaller. Okay, next. Now, we didn't go into a lot of detail with the kinetic molecular theory and to explain the laws, and I think I should do some of that now. In order to explain pressure, pressure is a force per unit area, correct? Force per unit area. Well, if the unit area is the same, then the force is related to the impact of particles against the walls of the container. So if we have a container here and we've mapped out an area, then the forces are going to be a certain amount at a given pressure. But if we increase the pressure, say we decrease the volume and leave the area the same, then you've confined those particles to a smaller area. There's the same number of particles, but the pressure is increased because you have more impacts per second on that same area because you've squeezed the particles into a smaller volume. That's the kinetic molecular theory explanation for a change in pressure when we change the volume. Now, how about volume and temperature? Volume and temperature. If we increase the temperature, we're increasing the kinetic energy, the average kinetic energy of the particles in that container. And if the same pressure is holding them down, then as they strike the plunger with more force, it will apply a higher pressure and drive it up until the pressure is equalized again. So that explains Charles' law, Boyle's law, Charles' law. How about Avogadro's law, volume and moles? If we have the same volume and the pressure and temperature are fixed, but we put more moles in there, we've got more gas at the same temperature, and each one of those particles is striking the surface with the same force, but there's more of them. So in order to equalize the pressure, then the volume has to increase until you decrease the number of impacts to what they were before you added the amount of gas. Okay, so that's the kinetic molecular theory quick explanation for the three gas laws that we've discussed. Now we're going to look at Graham's law of effusion or diffusion, either way. Graham's law of effusion. Diffusion is the movement of a gas through an open space from one place to another. It could be a liquid also, but we're sticking to gases right now. Effusion is the movement of a gas through an opening, say a small pore in a barrier. But the same principles apply for either one. That's why we can name it either way. Okay, so let's say we compare two gases, A and B, at the same temperature. Okay, V in this case stands for velocity, not volume. This is velocity. We should use a small v here, actually. So the ratio at the same temperature, actually the little t should be a big T. Let's see how we're developing that. Okay, velocity. Remember, velocity is distance per unit time. Okay, so little t is accurate. Little t is time. So if we multiply velocity times time, we get distance. Okay? So over the same period of time, the relationship between the velocity of A and velocity of B will be the distance that A moved ratio to the distance that B moved. And so if we do that ratio, the velocity of 1 over the velocity of 2 is equal to the distance 1 moved, distance 2 moved. Or A and B, excuse me, I should use A and B. A, B, there we go. Now, the velocity, remember the velocity calculation is square root of 3 RT over molecular weight of A. So that's what we've done. We've substituted in here that expression for 3 RT over the molar mass. And this is for and they're at the same temperature, and R is a constant, so the only variable here is A. All right, so we're just substituting this value. In other words, if this is equal to this, then and this is equal to that, then that's equal to that. Right? We're using the cumulative property again. Not cumulative property. My mind's gone blank. Transitive property. Transitive property. Okay, so now we're going to solve the equation, right? We can put everything under 1 square root, and that cancels this one and this one. And this is in the denominator here, this is in the denominator in the numerator. So what we get is molecular weight of B divided by the molecular weight of A. Right? This one flips into the numerator. I think that's what the animation shows. Yeah. Okay. So the relationship of the distance A traveled, ratio of A to B distance, is the same as the square root of the molar mass of B to the molar mass of A. Right? So the distance that A traveled could be bigger if molecular weight of A is smaller than B. Right? You divide this number by a smaller number, it makes the whole bigger. So that makes this bigger than that. So the lighter one is going to travel farther in the same amount of time. All right. And this can be used to determine the molar mass of an unknown gas. Remember when we were doing determining empirical formula and then using that to get the molecular formula, but we had to know the exact molar mass of the compound. But we didn't know the formula for the compound, so you can't calculate it. So this is one of the ways that you can get the molar mass without knowing what it is. All right. So here's our example. If we have hydrogen chloride gas, not the acid, not dissolved in water, but the gas, and we have ammonia, then when those two gases mix, they produce ammonium chloride, which is a solid, and it forms kind of a fog. So if you put a cotton ball here with hydrogen chloride gas in it, or hydrogen chloride liquid, and then you have ammonia over here,
then they're going to diffuse like that and meet somewhere in the middle. And when they meet in the middle, they'll form ammonium chloride and form a fog. And you can see where they meet and measure the distance that each traveled and ratio the two distances. All right, that's what we're getting at here. All right. So if we ratio the distance that ammonia travels to the distance that HCl travels, and by the way, what's the molar mass of ammonia? 14.01, 3.03 is 4071 grams per mole. How about HCl? It's 3545 plus 1.01, which is 6463, 3646. So it's over twice the mass of ammonia. So which one's going to travel the fastest? Ammonia is going to travel the fastest. So it's going to move faster. It's going to be over here somewhere before they meet. Okay. And we know from our previous formula that if we ratio HCl to ammonia, molar mass, then that's proportional. The square root of that is proportional to the distance that ammonia travels divided by the distance that hydrogen chloride travels. If we substitute those values that we just determined, then the ratio of the two distances is 1.5. So if this whole distance is 2, then they'll meet somewhere right in here. All right. So the distance that hydrogen chloride travels in a 150 centimeter tube will be 60.9 centimeters here. And then the rest will be the distance that ammonia traveled. Okay. All right. So let's say ammonia travels, we put ammonia in one end and we put an unknown in this end, right? Some gas we don't know. But we do know that it will react with ammonia. And we're given the distance that is traveled. The tube is 120 centimeters long, and after we wait about 5 minutes, and then the smoke ring appears at 87.9 centimeters from the ammonia. So 87.9 over here forms, and we can ratio the two, just like that, the distance, and set that equal to our equation where we know the molar mass of ammonia, but we don't know the molar mass of the other compound. And solve for the other compound. Okay, so we end up with 127.6 grams per mole as our unknown. Right. If we know that it's a hydrogen compound of any of these halogens, then we can take the molar mass of each of the halogens and figure out which one it is. All right. I think we're almost at the end. Graham's law of diffusion was used for practical purposes during World War II. The problem in the Manhattan Project was that uranium that we needed to make the bomb occurs in primarily 2 isotopes. Most of them are here. About 0.5% is U-235. So what was done was these were converted to the hexafluoride. That allowed us to vaporize them at much lower temperature. And then this mixture was forced through Teflon sieves with very, very small holes in them. And the one that went through the fastest was the lightest. So on the other side of the barrier, right, these go in here, this is enriched in U-235. Only enriched by a tiny amount. So what they had to do was they set up a series of these things, thousands of them. And each time that passed through a sieve, and then they recycled this stuff here as they pushed it through, they recycled it, and kept pushing it through. Eventually, at the very end, they ended up with a gas, a fluoride gas of U-235 that was sufficiently enriched to make the bomb. They just had to convert it back to the metallic uranium in small enough quantities so that it didn't go critical, obviously. Okay, so there it is. U-235 is only 0.72%. Okay, and there's the differential in the velocities of motion, 1.0043, so it's not much. That's why they had to do it over and over and over again. The thing that made it possible was the development of Teflon, because the hexafluoride compound of uranium was extremely corrosive. They couldn't use even stainless steel. So the invention of Teflon in 1938 at DuPont was what allowed them to make these sieves that were impervious to the fluoride gas. There was a plant. I used to live in Oak Ridge as a kid, and there was a plant there called K25. And you can see there this aerial view. That plant was huge. It would take about 20 minutes. You could drive around the perimeter. They had a high fence with barbed wire and armed guards everywhere. But you were allowed to drive around the fence and just look at the plant. So my family being not so rich, our means of entertainment was to hop in the car and drive around the plant. And there was more than one. There were different plants, but this one was a good one. And it would take you 20 minutes to drive around the thing. It had 44 acres covered under roof. And most of that was composed of those Teflon filters that were being used to separate the uranium-235 from the uranium-238. There's the website. If you want to see more about the history of that plant, then you can go to that website and you get all the details you want. That was one way to separate them. Okay, the last thing we want to talk about is what are real gases like? We know that ideal gases, we have to assume that there's a point volume. They stay gases at all temperatures and pressures. They don't interact with each other. They collide in an elastic fashion, which is what I meant by billiard balls. They just smack and bounce off. Conservation of energy. Real gases, however, they do have a volume, a measurable volume for each of the gas particles. They can liquefy if you compress and chill them enough, which means that they interact with one another, right? If they don't interact with one another, then it doesn't matter how much you pressurize them, they're not going to attract one another sufficiently to make a liquid or a solid. So they do interact with one another. And they collide in an inelastic fashion. In other words, when they smack each other, momentum is conserved, but energy is not. So, a pretty smart guy named van der Waals developed an equation that corrected for various changes due to the fact that they're real gases. And this formula, you really only need to deal with it and use it. It's a modification of the ideal gas equation, PV equals nRT. And it corrects the pressure and the volume terms.
Volume correction is fairly innocuous. The pressure correction is a little more involved. But the only time you need to use those corrections is if you're actually an engineer and you're trying to assess gas-related changes at extreme pressures and volumes. Right? You squeeze it to a small volume, you increase the pressure to a high value in certain reactions, then you need to correct, and that's what these changes will do. Right, and that's all you need to know. Just the difference between an ideal and a real gas. You may remember the fellow's name, Van der Waals. Right, that's an important name. Okay, that's it. We're done for today, and the recording will be up this weekend.